You flip a switch and your house lights up. Solar panels on your roof did that, but nobody tells you how those black rectangles actually turn sunshine into the thing running your laptop right now. Silicon atoms getting smacked by photons at the speed of light, electrons ripping free from their bonds, current flowing through metal grids thinner than human hair. This is not magic. This is quantum mechanics meeting industrial engineering, and every method works differently. Which technology dominates the market? Which one just broke efficiency records in 2024? What happens when you stack multiple junctions on top of each other? Let's break down every single way these devices convert light into electricity, backed by numbers from the labs that built them. A 19-year-old physicist named Edmond Becquerel is running experiments with metal electrodes dunked in conductive solution. Light hits the electrode. Current jumps. He writes it down in Comptes Rendus de l'Académie des Sciences. That is the first documented photovoltaic effect, the moment humans discovered that light could push electrons and create electricity. Move forward to 1884. Charles Fritz builds the first actual solar cell, selenium coated with a thin film of gold. Efficiency? Pathetic, barely 1%. But it worked. Jump to 1954. Bell Telephone researchers cracked the code with silicon. The first practical photovoltaic cell achieves 6% efficiency. Space programs grab it immediately because weight matters up there, and by the late 1950s, PV cells are powering US satellites. Fast forward to today, and silicon solar cells dominate over 90% of the commercial market, with lab examples hitting 27.1% efficiency. Department of Energy's Solar Energy Technologies Office published in their Solar Photovoltaic Cell Basics documentation in 2024, and the National Renewable Energy Laboratory's efficiency charts verified by institutions like Fraunhofer, ISE, and STE. These are the primary testing labs that certify world records, not generic claims. Now back to the information. Silicon makes up over 90% of all solar panels sold globally because it works and it scales. The physics is straightforward but brutal. A photon with enough energy hits a silicon atom. That photon must carry at least 1.1 electron volts of energy, which is silicon's band gap. If the photon has less energy, it passes right through. If it has more, the excess energy turns into heat and gets wasted. When the photon hits with the right energy, it knocks an electron loose from the valence band into the conduction band, leaving behind a hole. Now you have an electron-hole pair. Here's where the engineering starts. Pure silicon is useless for solar cells because electrons and holes just recombine immediately. So manufacturers dope the silicon. They take a wafer of lightly p-type silicon, which is doped with boron to carry positive charge, and they create a thin, heavily n-type layer on top, doped with phosphorus to carry negative charge. That creates a p-n junction, an electric field built right into the material. Electrons flow toward the n side, holes toward the p side. The electric field at the junction separates the charges and prevents them from recombining. Solar-grade silicon must hit 99.9999% purity, 6 nines. That silicon comes from sand, refined through multiple chemical processes until impurities are nearly gone. The Czochralski method dominates monocrystalline production. A seed crystal gets dipped into molten silicon at 1,414 degrees Celsius, then pulled upward at 0.5 to 1.2 millimeters per minute. The result is a cylindrical ingot weighing 300 to 450 kilograms, 8 to 12 inches in diameter, grown over 40 to 60 hours. Those ingots get sliced into wafers 180 to 200 micrometers thick, using wire saws with abrasive slurry. The sawing process damages the surface, so wafers go through chemical etching with heated sodium hydroxide or potassium hydroxide solution to remove that damage and smooth the surface. Then comes texturing. Anisotropic etching with potassium hydroxide or sodium hydroxide creates micrometer scale pyramids on the silicon surface. These pyramids reduce reflectivity below 10% by causing light to bounce into the wafer at angles rather than reflecting off. The pyramids are typically 5 to 10 micrometers in height, with a base width around 10 micrometers. This takes 8 to 12 minutes per batch and consumes 2 to 4 liters of chemicals per wafer. Separation happens. Then metal contacts go on. Silver paste gets screen printed onto the front in a grid pattern with line widths around 120 micrometers. These fingers collect electrons. The back gets a full aluminum layer to collect holes. An anti-reflection coating of silicon nitride goes on the front to increase light absorption further. The whole assembly then gets laminated with ethylene vinyl acetate and glass at 150 degrees Celsius for 20 minutes. Final result? Monocrystalline silicon cells hitting 22 to 24% efficiency in commercial production. Single crystal. This costs less because the process is simpler, but efficiency drops to 15 to 18% because grain boundaries scatter electrons and reduce current flow. The cells look different too, with visible crystal patterns, instead of the uniform black of monocrystalline. In the crystal lattice, those electrons form covalent bonds with neighboring atoms. That is the valence band. The conduction band sits higher in energy, separated by the 1.1 electron-volt band gap. At room temperature, almost no electrons have enough thermal energy to jump that gap, so pure silicon barely conducts. Doping changes this. Phosphorus has 5 valence electrons, one more than silicon. When phosphorus replaces a silicon atom in the lattice, that extra electron sits loosely bound, requiring only about 0.05 electron volts to free it into the conduction band. That is an N-type doping. Boron has 3 valence electrons, one less than silicon. It creates holes, empty states that act like positive charges. That is P-type doping. Electrons from the N side diffuse into the P side and recombine with holes. Holes from the P side diffuse into the N side and recombine with electrons. This creates a depletion region a few micrometers wide where no free charges exist. But the immobile dopant atoms are left behind, positive on the N side, negative on the P side. The charge imbalance creates a built-in electric field pointing from N to P. This field is permanent, locked into the structure by the doping profile. Now light hits, a photon with energy above 1.1 electron volts, slams into a silicon atom in or near the depletion region. Electron jumps to conduction band, hole left behind. The built-in electric field immediately sweeps the electron toward the N side and the hole toward the P side before they can recombine. That separation is current. Connect a load between the front and back contacts and electrons flow through the external circuit from N to P, powering whatever device you plugged in. The voltage generated depends on the band gap and the quality of the junction. For silicon, that is typically 0.5 to 0.7 volts per cell. To get higher voltage, you connect cells in series. A typical residential solar panel has 60 cells, wired in series producing around 36 volts at peak power. Some electrons and holes recombine before the electric field can separate them, especially if there are crystal defects or impurities. Some current gets lost in the resistance of the metal contacts and the silicon itself. Add it all up, and even the best silicon cells under standard test conditions, 1,000 watts per square meter of light at 25 degrees Celsius, convert only about 26 to 27% of incoming solar energy into usable electricity. That is the practical limit approaching the Shockley-Queisser limit of 33.5% for single-junction cells, a theoretical ceiling calculated in 1961 that accounts for unavoidable thermodynamic losses. Plastic or metal? 3 main types dominate. Cadmium telluride is the second most common photovoltaic material after silicon. CDT cells can be made using low-cost manufacturing processes because cadmium telluride can be deposited directly onto glass substrates at relatively low temperatures. The band gap is 1.5 electron volts, nearly ideal for the solar spectrum. Commercial CDT modules from manufacturers like First Solar achieve efficiencies around 18% with lab cells, pushing past 22%. The entire thin film stack is only a few micrometers thick, compared to 180 micrometers for crystalline silicon wafers. That saves material and reduces weight. But cadmium is toxic, so end-of-life recycling becomes critical. First Solar runs recycling programs collecting 90% of cadmium from returned modules. The advantage is CIGS cells can be deposited on flexible substrates, making them useful for curved surfaces or portable applications. Lab efficiencies have reached 23.4%. The complexity of combining 4 elements makes scaling to mass production harder than CDT. Both materials require more protection than silicon to survive outdoors long term because thin films degrade faster under moisture and heat stress. Amorphous silicon is the third thin film option. Unlike crystalline silicon, amorphous silicon has no ordered crystal structure. Atoms sit randomly arranged. This disrupts electron flow and lowers efficiency to around 6 to 10% in commercial products. But amorphous silicon absorbs light much more strongly than crystalline silicon because the disordered structure allows more optical transitions. That means a layer only 1 micrometer thick can absorb most of the incoming light. Manufacturing costs drop dramatically. Early thin film solar calculators and watches used amorphous silicon. Modern approaches stack multiple amorphous silicon junctions with different band gaps to boost efficiency into the 10 to 12% range. These triple junction amorphous silicon cells were produced by companies like Unisolar, now defunct, but the technology demonstrated that stacking junctions improves performance. The term perovskite refers to materials with a specific crystal structure, typically ABX3, where A is an organic cation like methylammonium or formamidinium, B is a metal cation like lead, and X is a halide like iodine or bromine. Methylammonium lead iodide is the most studied. The band gap sits around 1.5 to 1.6 electron volts. Tunable by swapping elements, manufacturing is shockingly simple compared to silicon. You can make perovskite films by spin coating or blade coating solutions onto substrates at low temperatures, often below 150 degrees Celsius. No high temperature furnaces, no vacuum chambers, no expensive epitaxial growth. Just dissolve the precursors in a solvent, spread it on glass, let it dry and crystallize. The result is a thin film a few hundred nanometers thick that absorbs light incredibly well and converts it to electricity. LONGi Green Energy broke records throughout 2024, hitting 34.6% efficiency in June with a 2-terminal perovskite silicon tandem cell verified by the European Solar Test Installation. That jumped to 34.85% in April 2025. The top perovskite layer has a band gap around 1.7 electron volts and absorbs high energy blue and green photons. The bottom silicon layer has its 1.1 electron volt band gap and absorbs lower energy red and infrared photons. By splitting the spectrum, you reduce thermalization losses where excess photon energy turns into waste heat. The two layers work together, each optimized for its portion of the spectrum, and the combined efficiency smashes past what either material could achieve alone. Early perovskite cells degraded within hours when exposed to moisture, oxygen, or heat. The organic cations are volatile and the crystal structure breaks down easily. Researchers attacked this from multiple angles. Northwestern University announced in November 2024 a new imidinium-based coating that replaces the less stable ammonium ligands. The imidinium-coated cells achieved 26.3% efficiency and retained 90% of initial performance after 1,100 hours of testing at elevated temperature. That is triple the T90 lifetime compared to older ammonium-coated versions. Another approach uses fully inorganic perovskites like cesium lead iodide, CSP by 3, which has no organic cations to degrade. These sacrifice some efficiency, topping out around 15 to 18%, but gain durability. A team from Hanyang University and Kookmin University in South Korea demonstrated flexible quantum dot cesium lead iodide cells hitting 12.7% efficiency in March 2024, the highest reported for flexible quantum dot solar cells, retaining 94% efficiency after 500 bending tests. Perovskites are not commercial yet at scale. The technology is still moving too fast. Every few months someone breaks another record, but pilot production lines are running. Oxford PV in the UK announced commercialization plans in September 2024. Utmolite in China reported 18.1% efficiency on 0.72 square meter perovskite modules in March 2025, a global record for modules that size, with a 150 megawatt pilot line supplying commercial projects across multiple Chinese provinces. The next 5 years will determine if perovskites can survive 25 years outdoors and match silicon's reliability. If they can, the solar industry will look very different because the cost per watt could drop significantly below current silicon prices. Quantum dots are semiconductor nanocrystals typically 2 to 10 nanometers in diameter, so small that quantum mechanics dominates their behavior. At this scale, electrons cannot occupy continuous energy levels like they do in bulk materials. Instead, they are confined to discrete energy states like electrons and atoms. That is why quantum dots are called artificial atoms. The energy levels, and thus the band gap, depend entirely on the dot size. Bigger dots have smaller band gaps and absorb longer wavelengths. Smaller dots have larger band gaps and absorb shorter wavelengths. You can tune the band gap just by changing the synthesis duration or temperature during production. That tunability makes quantum dots attractive for solar cells because you can engineer them to absorb specific portions of the solar spectrum. Quantum dots create an intermediate energy band between the valence and conduction bands of the host material. This enables two-step photonic transitions. A low-energy photon that would normally pass through a regular solar cell can excite an electron from the valence band to the intermediate band. A second photon then excites that electron from the intermediate band to the conduction band. This two-step process captures sub-band gap photons that single-junction cells waste, broadening the absorption spectrum. Theoretical calculations suggest quantum dot solar cells could exceed the Shockley quasar limit and approach 66% efficiency by utilizing hot photogenerated carriers to produce higher voltages or currents. As of 2022, quantum dot solar cell efficiency reached 18.1%, achieved by a team at Ulsan National Institute of Science and Technology in South Korea. The breakthrough came from a novel ligand exchange technique published in Nature Energy in January 2024. Quantum dots synthesized in solution have long organic ligands attached to their surfaces to prevent aggregation. These ligands are insulators and block charge transport between dots. To make working solar cells, you need to replace the long ligands with short ones that let electrons hop from dot to dot. The UNIST team used alkyl ammonium iodide-based ligands that enabled organic cation-based perovskite quantum dots with exceptional stability and suppressed internal defects. The cells retained efficiency even after long-term storage, a major improvement over previous attempts. Another group from the University of Potsdam and the Chinese Academy of Sciences combined perovskite quantum dots with organic absorbers in December 2024, reaching record-level efficiency for that architecture published in Nature. The spacing between dots affects electronic states and transport properties. Array shape, order, disorder, and dot orientation all influence performance. Defects accumulate at interdot junctions. But the potential remains enormous because quantum dots can be solution processed like perovskites, deposited by spin coating or inkjet printing at low cost and low temperature. Researchers continue pushing efficiency higher while working on stability and scaling to larger area devices. The market for quantum dot solar cells was valued at $910 million in 2024 and is projected to hit $3,174 million by 2033, a compound annual growth rate of 15.4%. If you value this level of technical depth with verified numbers from labs and journals, subscribe. Let us know in the comments where you are watching from. This research comes from peer-reviewed sources including Nature Energy, which published the UNIST quantum dot breakthrough in January 2024, and Science Direct, which tracks efficiency records through verified testing institutions. Back to the methods. Multi-junction solar cells. The Shockley-Kieser limit for single-junction cells is a hard wall at 33.5%, because a single band gap cannot optimally convert the entire solar spectrum. High-energy photons waste energy as heat. Low-energy photons pass through unabsorbed. The solution is stacking multiple junctions with different band gaps, each tuned to absorb a specific slice of the spectrum. Multi-junction cells divide the solar spectrum into bins, where each subcell operates closer to its thermodynamic efficiency limit. A theoretical stack with infinite junctions could reach 86.8% efficiency under highly concentrated sunlight. Solar energy systems, with a 4-junction concentrating photovoltaic cell operating at 665 suns concentration. That beat the previous 47.1% record from 2019, when the National Renewable Energy Laboratory demonstrated an inverted metamorphic 6-junction cell. These are not your rooftop panels. Multi-junction cells use expensive 3V compound semiconductors grown by molecular beam epitaxy or metal organic chemical vapor deposition. Materials include gallium indium phosphide, gallium arsenide, and germanium, chosen because their crystal structures lattice match, meaning atoms line up when layers stack. Mismatch creates defects that kill performance. Light that passes through hits the second junction with a lower band gap, around 1.4 electron volts, absorbing green photons. The third junction, at 1.1 electron volts, takes red light. The bottom junction, at 0.7 electron volts, catches near-infrared. Each layer converts its assigned wavelengths with minimal waste. The subcells connect in series through tunnel junctions, ultra-thin, heavily doped layers that let current flow between junctions with almost no resistance. Because they are in series, the same current must flow through all junctions. So designers must current match by tuning the thickness and band gap of each layer, so they all generate the same photocurrent. Get it wrong, and the weakest junction limits the entire device. Concentrations of 300 to 1,000 suns. This boosts efficiency because the cell operates at higher light intensity, where voltage increases logarithmically while current scales linearly, improving the power output per unit area. At 1,000 suns, a 4-junction cell can deliver over 45% efficiency. The catch is cost. These cells run hundreds of dollars per square centimeter. They make sense for space applications where launch costs dominate, and high power to weight ratio matters more than dollars per watt. On Earth, they work for utility-scale concentrated solar installations in deserts, where direct sunlight is plentiful, and tracking systems can keep lenses focused on the sun, but they cannot compete with silicon for residential or commercial rooftop installations because the optics and tracking add too much complexity and cost. Q-Cells in Korea announced a 28.6% efficiency on a full M10-sized module, 330 square centimeters, in December 2024. That size can scale to mass manufacturing. Jinko Solar reported 33.84% for perovskite silicon tandems on N-type wafers. These numbers showed tandem technology is commercial ready. The question is whether manufacturers can scale production while maintaining high yields and reliability over 25-year lifetimes. The stack used a 1.84 electron volt perovskite top cell, a 1.52 electron volt perovskite middle cell, and a 1.1 electron volt silicon bottom cell. The middle cell was the breakthrough, requiring stable alpha phase from a modinium lead iodide perovskite with no wrinkles, cracks, or pinholes. The device hit an open circuit voltage of 2.84 volts and short circuit current of 11.6 milliamperes per square centimeter. Non-encapsulated devices retained 96.6% efficiency after 1,081 hours stored in the dark at 85 degrees Celsius. Another team at the University of Sydney fabricated a 16 square centimeter triple junction cell that achieved an independently certified steady state efficiency of 23.3%, the highest for a large area device passing the International Electrotechnical Commission's thermal cycling test with 95% efficiency retained after 407 hours of continuous operation. Bifacial panels fix this by putting photovoltaic cells on both front and back. The front captures direct sunlight like any panel. The back captures reflected light, called albedo. The additional energy capture depends on surface reflectivity, installation height, tilt angle, and shading. White gravel reflects over 80% of incident light. Grass reflects 23%. Snow reflects 90%. Concrete around 50%. The higher the albedo, the more the rear side contributes. Location. A study by Long East Solar found bifacials increased efficiency by 11% on average compared to conventional systems. Burns and McDonnell measured surfaces, finding white surfaces reflect more than 80%, while grass reflects only 23%. Painting a white surface under the panels significantly boosts rear side generation. Ground-mounted systems benefit most because there is space underneath for reflected light to reach the rear. Elevated mounting 2 to 4 feet above the ground works well. Vertical installations produce 2 energy peaks per day, morning and evening, when low-angle sunlight hits both sides. Rooftop bifacials work only on flat roofs with reflective membranes. Traditional sloped rooftops provide minimal rear side gain because the panel sits too close to the roof, and the roof surface is usually dark asphalt or tile. Floating solar farms on water benefit from water's reflective properties, especially early morning and late afternoon when sun angle is low. Snow-covered ground provides massive gains. A Canadian experimental study published in September 2024 in EPJ Photovoltaics found that when snow accumulated to 2 centimeters and covered the front completely, the rear side alone generated measurable power. When snow depth reached 13 centimeters but temperature rose from -10 to plus 5.5 degrees Celsius, snow slid off the front and modules returned to normal operation, demonstrating bifacials can continue generating in conditions that disable monofacial panels. Installed capacity jumped from 97 megawatts globally in 2016 to over 2,600 megawatts in 2018. Wood Mackenzie Power and Renewables projected 20,000 megawatts by 2024. The International Roadmap of Photovoltaic estimated bifacial market share would grow from 12% in 2019 to nearly 60% of total global installations by 2029. Major manufacturers, including Q Cells, Canadian Solar, Jinko Solar, and Longi, produce bifacial modules. The U.S. kept tariff exemptions on bifacial panels in 2022, making them cost competitive for utility-scale projects. Panel construction uses double glass layers instead of glass and polymer backsheet, adding weight but dramatically improving durability and resistance to environmental stress. N-type cells, rather than P-type cells, work better in bifacials because N-type has less light-induced degradation and better temperature coefficients. PERC technology, passivated emitter and rear cell, combined with bifacial design, creates high-efficiency modules exceeding 22% front side efficiency, with the rear adding another 2 to 6 percentage points depending on albedo. Concentrator photovoltaics and advanced silicon. Fresnel lenses, or parabolic mirrors, focus sunlight 300 to 1,000 times onto tiny multi-junction cells. At 1,000 suns, concentration of 4 junction cell delivers over 40% efficiency. The cell costs hundreds per square centimeter, but covers 1,000 times its area through optics. Current scales linearly, voltage logarithmically, boosting power output. Series resistance becomes critical at high current. Passive heat sinks keep temperature below 85 degrees. The catch? Concentrators need direct sunlight. Cloudy days produce nothing. Dual axis tracking keeps lenses aligned as sun moves 15 degrees per hour. This limits deployment to sunny deserts with high direct normal irradiance, exceeding 2,000 kilowatt hours per square meter yearly. Soitec built installations in California and South Africa using 493 times concentration. PERC accounts for over 70% of global production by 2024. TOPCon pushes further with ultra-thin 1 to 2 nanometer silicon oxide topped by phosphorus-doped polysilicon. Electrons tunnel through while oxide blocks holes. Lab cells exceed 25%, commercial hits 24%. Jinko Solar, Longai, Trina. Solar invested billions in TOPCon lines starting 2022. Silicon heterojunction uses amorphous silicon passivation, reaching 26% with excellent temperature coefficients. Low processing temperature below 200 Celsius enables bifacial designs. Each technology fills specific roles. Silicon dominates utility scale. Perovskite tandems chase records. Multi-junctions power spacecraft. Bell Labs builds the first working silicon cell in 1954 at 6% efficiency. Shockley and Quaser calculate the 33% limit in 1961. Gretzel invents dye-sensitized cells in the 1990s. Perovskites explode from 3.8 to 26.7% in 15 years. Tandem cells smash through 34%. Multi-junction cells hit 47.6% under concentration. Every method converts light to electricity, but the mechanisms diverge. Silicon relies on p-n junctions and doping. Perovskites use simple solution processing and tunable band gaps. Quantum dots exploit size-dependent quantum confinement. Organic cells print on flexible substrates. Multi-junction stacks split the spectrum across layers. Each technology fills a different role. Silicon dominates residential and utility scale. Perovskite tandems chase higher efficiency. Multi-junctions power satellites. Organic cells target niche applications. The diversity is the point. No single technology wins everywhere. The question is not which method is best. The question is which combination of technologies will power the grid when fossil fuels are gone. In 2024, researchers at Longy pulled a polysilicon passivated contact cell from a test rack that had been running outside for 3 years. Efficiency drop? Less than 2%. The aluminum oxide interface showed no degradation under electron microscopy. Zero delamination. In the Fraunhofer ISE vault sits a 4-junction concentrator cell that delivered 47.6% efficiency at 665 suns in May. 2022. That cell used gallium indium phosphide, gallium arsenide, and germanium junctions, wafer bonded together, a fabrication method so precise the lattice mismatch stayed below 0.1% across the entire structure. In Ulsan, South Korea, a quantum dot solar cell synthesized with alkyl ammonium iodide ligands retained full efficiency after 6 months stored at room temperature in ambient air, something previous quantum dot cells could not do for 6 days. At Northwestern, a perovskite cell coated with amidynium ligands survived 1,100 hours at 85 degrees Celsius in the dark and came out at 90% efficiency. At the University of Sydney, a triple-junction perovskite cell passed 400 cycles from minus 40 to 85 degrees Celsius, the IEC thermal cycling test that simulates 25 years of real world. Temperature swings. It will be a tandem cell, perovskite on silicon or perovskite on CIGS, delivering 30% efficiency, half the thickness, flexible enough to curve over your car roof. It will cost 1/3 the price per watt because solution processing replaces expensive vacuum equipment. It will last 30 years because passivation layers and encapsulation chemistry finally caught up to the optoelectronic performance. Every method described here represents one path forward. The winning path is still being written in labs and factories right now, backed by billions in investment and thousands of researchers stacking atoms, tuning band gaps, and chasing that next 1/10%.